Falling Object Lab. The objective was to analyze the motion of a falling object and compare that to two different computer models based off of Newton's laws. The first computer model only accounts for the force of gravity. The second computer model accounts for the force of gravity and the drag force. Synopsis of results. Newton's laws correctly predicted the motion of the falling object in both models. Newton's laws. Newton's first law states an object in motion stays in motion and an object at rest stays at rest unless acted upon by an unbalanced force. Newton's second law is the math behind the law, and it states the final velocity is equal to the initial velocity plus the net force divided by the mass times the delta t, or change in time. The forces at work in this lab are gravity. This force of attraction between two bodies is proportional to the mass of those objects and inversely proportional to the distance between them squared. In this lab, we are looking at acceleration of a falling object due to the force of gravity on the object by the Earth. The drag force is a force acting opposite to the motion of the object, which is proportional to the velocity squared. In this lab, the drag force is in the plus y direction since the object is moving in the negative y direction. Newton's laws in our lab. The falling object is being acted on by an unbalanced force or forces. So according to Newton, its velocity is changing or it is accelerating. The system is a golf ball falling in the minus y direction from the origin, which is 0, 0, 0. The surroundings are the air and the earth. There are two different types of forces, the contact force, which is the drag force due to collisions with the air, and it's taken into account in the second computer model, and the non-contact force of gravity due to the attraction between the object and the earth, and it's taken into account in both computer models. Collection and analysis. The motion of the golf ball was taken with a flip camera and imported into Tracker. Tracker was used to analyze the motion of a golf ball frame by frame. The motion began at the origin, 0, 0, 0, and traveled in the negative y direction. It was assumed the force of gravity, g, was equal to negative 9.8 meters per second squared. The object's position from the video was then compared to two different computer models that were based on Newton's laws. In computer model 1, gravity was the only force acting on the ball, and in computer model 2, gravity and drag were the forces acting on the ball. Here's an image showing the motion of the golf ball. The data was then imported into a spreadsheet and compared to the two models. The first computer model. The code highlighted in pink shows that gravity is the only force acting on the ball in this model. And this can be seen because F net is equal to W, where W is the weight. The code highlighted in blue shows Newton's second law. The net force in computer model 2. The code highlighted in pink shows the computer model 2 takes into account gravity and drag. And you can see that because F net is equal to W plus Fd, or the weight plus the force of the drag. The drag coefficient B was determined to be very small for the golf ball. B was equal to 0.001 and drag was equal to B times the velocity squared. The code highlighted in blue shows Newton's law in the second computer model. Terminal velocity was calculated from the second computer model. We know that the net force is equal to the weight plus the force of drag. Now, force of drag is equal to B times velocity squared. So as the velocity increases, force of drag increases. So we will get to the time when the force of drag equals the weight, and then the velocity will stop increasing, or you will reach terminal velocity. The ball would reach terminal velocity more quickly if the ball was thrown downwards instead of just dropped. B again was determined to be 0.001, and the terminal velocity was calculated to be 98.9 meters per second. Here are the three different sets of data on one graph. You can see the experimental data are the blue pluses, the model with gravity is the green, and the model with drag and gravity is the yellow, which you can't really see because it's right on top of the green because B was very, very small because the fit was pretty good. Conclusion. The data from the experiment matched the projected position for both models. This was surprising considering drag was not taken into account in the first computer model. And when drag was taken into account, the drag constant B was so small it really made no difference in the fit of the graph. Reasons for this could be a golf ball's dimple design minimizes drag. The image on the film was also very blurry, so maybe some of the measurements were inaccurate, and I suspect this is very true. The time it took the ball to fall was too short to show the effects of drag on the golf ball.